here we are again. It's the physics video lecture. Physics 4B video lecture 9. So we've moved on into electricity and magnetism. Amazing subject, a lot of great stuff to do. And I'll start with a bit of a review and add some stuff. So we call it electricity and magnetism, but for the moment we're just doing static electricity. So I'll go ahead and start that way and remind us we have electric charge as our new quantity. Up until now it had all been kilograms, meters, and seconds, and now we have the coulomb. So we have the, use the letter Q for example, the unit is the coulomb, and charge comes in positive and negative. So we have the law that like charges repel, unlike charges attract, and there is this force law due to Coulomb. Coulomb's law is that force is proportional to the product of the two charges, and in this case we're talking about point charges for the moment, and elementary charges are basically point charges. So the proportional to the product of the two charges divided by the separation distance squared. It is a central force law. Okay, if they're both positive, then you have a repulsive force, or if they're both negative as well. Say you discovered this via static electric experiments. So there are a few things to add to that now. We had done a couple of examples with this, and we'll continue to do those. Just to kind of get a list of fundamental principles and concepts going, it is found that charge is conserved. So what does that mean? Conservation of charge means that the total amount of charge is constant. And say if you have a neutral body, then there's a positive and negative charge that cancels each other out in magnitude, so that you'd have a neutral body with zero charge, even though there's some great number of pluses and minuses. So I could just kind of draw a bunch of pluses and minuses. I have to make sure 1, 2, 3, 4, 1, 2, 3, 4, and this net charge of 0 is going to be conserved and remain constant. So it's possible to remove some minuses from this body here, and then it will have a net positive charge, but we won't have created any charge. We'll have just moved some around. So we can imagine charge conservation, and we'll assume the total charge is 0 net charge. So that's one important principle. See what the book has to say about that. And then there's the quantization of charge. So we have these elementary charges of positive and negative E. I wrote those up on the board last time, the electron and proton charge. Now from the standpoint of this class, that's what we have, okay? Plus E and negative E. Oops, careful there. Positive electron charge, negative electron charge. But from the more fundamental theory, there are actually fractions of charge, but they never appear. So the charges that appear are always plus and minus the electron charge. So we're going to stick with that as the quantization of charge. And I also have to talk briefly about conductors and insulators. So So metals tend to be good conductors, and what that means is charges can move freely. So continuing our numbers here, conductors, we mean electric conductors, they allow charge to move freely. Charges move freely. Insulators, charges do not move freely. So in insulators, charges are essentially fixed. If you add some charges to an insulator, they won't move around that much. Okay, so charges move freely versus insulators where that's not the case. But now if we look at the atomic structure of an insulator, we get to an interesting phenomenon called polarization. So now let's suppose we have here an insulator. So this is an insulator. Could be a piece of wood, okay? Metal's a good conductor. Could be a piece of wood. And yet in that piece of wood, there are innumerable positive and negative charges, in the atomic structure. So that's all mixed up, and we're assuming that the whole thing is neutral because the number of positive and negative charges in this object is equal. Okay. So what happens though? So now I'm just going to randomly have plus and minus, and I'm not going to try too hard there. Neutral insulator, but suppose we now bring a strong positive Q right here. What's going to happen? We bring a strong charge to this neutral body. The charges that comprise the matter in here, the positive ones will be repelled and the negative ones will be attracted to this strong charge. And the polarization that occurs, which is to say the separation of charge, without it actually leaving this insulator, so what gets attracted to a positive is negatives, and what gets repelled from a positive is the positive. So you get what's called charge polarization within the material, and the material now, because the charge is polarized, will actually, even though it was neutral, it'll be attracted to this positive charge here. Same thing will happen with a negative charge. So that's something where we have some interesting demonstrations of, I may bring around next time. But the phenomenon is charge polarization. Polarization, okay. So that happens, again, when you bring a strong charge, could be done with negative as well, in the vicinity of an insulator. It acts on the charges that are part of the insulator. Okay, continuing on with our list. We already did the comparison of Coulomb and Newtonian gravity. So now I can come into the topic at hand, and that is the electric field. The electric field. And what we imagine is, suppose we have some positive charge over here, and we're going to just bring what we call test charges over here and see what happens to them. So if I bring a negative test charge over here and let go, it's going to be attracted. If I bring a positive test charge over here, it's going to be repelled. And what we do is we say there is an influence of these charges out here in space, and we call that the electric field. So over here there's going to be E field vectors pointing here such that I bring up a test charge and it'll experience a force. So this is the electric field, And let's just say a test charge experiences a force. Electric field, E field, such that a test charge Q0 experiences a force. So all we have to do now is do this. Force is equal to Q0 E. And that actually, we use that to define the E field. So the electric field is just the electric force divided by a charge. So we immediately can find out what the units of the electric field are. Units, and again, it's always put the square bracket around there, and what do we have? Newtons per coulomb. So newtons per coulomb. Good. So we'll immediately talk about the electric field of a single point particle. And that will be identical almost to just talking about Coulomb's law as we did last time. Go ahead and do that. We are still numbering, so we've got a 9 coming up. Well, let's call this, for our example, the electric field of a positive point charge. E field of a positive point charge. So now we've got our point charge here, Q, and we're out at this point here, and we'll put our little Q0 here. And what about the direction of the force? Well, the direction of the force is in that direction if these are both positive charges. Okay. So we could take a point charge over on this side. Okay. And then, so what I'm drawing now is the E field vector. Then E would be pointing in this direction, because if I take this positive test charge over here, it would be repelled. So the law that we're talking about, of course, is F is equal to K Q0 over R squared. So E, what's E? F over Q0. So E is equal to KQ over R squared. So for a point charge is the field, and the field and the force, we're talking almost the same thing. It's just that we don't have the charge here. So what we do is we say the field, it's there, but we feel it when we actually put a charge there, and then it'll fly away or experience a force. So the E field of a point charge, of a positive point charge, is directed radially outward. So I'll go ahead and put this as point 10. So here's now my positive point charge at the origin. And at any point, and this is true in 3 dimensions, okay, but 2 dimensions of the board, at any point, the E field is directed outward. So now, do the arrows get longer or shorter at the greater distance? Well, 1 over R squared is the law, right? So they get shorter. So if I were to say, well, I've got arrows of a certain length at a certain distance here, then when I'm further away, they're shorter. Okay. So good. Radially outward Now what about the field here? Let's go ahead and label this. E field, electric field, positive point charge. Good. What about a negative point charge? Negative point charge will be exactly the same, except the arrows are all directed towards the origin. So let's just put this as a note. You guys can add a picture. You can add a picture to your notes. I'm just going to write for the negative point charge. Direction is, towards the center. Direction is reversed. So yeah, you can use everything you've learned about vectors last semester to add arrows. Because remember, vectors add like arrows, so you can add the forces or you can add the fields just using your vector addition. I had an interesting problem on the last homework that maybe I'll say something about. So we've got these fields here. Maybe I'll make a note of that. So point 11, they go towards the center. Let's send this up here. So the terminology for this addition of vectors is called the superposition of fields. Okay, you just add the vectors. And I think I'll look up that homework problem and do a little picture of it. So 11, 12, superposition of fields, I-E-L-D-S, superposition of fields, and I'll just write here vector addition. Now this problem that I remember in the book was problem 35. Didn't I assign that? Yes, I did. So chapter 21, problem 35. Let's draw a picture of it. What chapter is this? Chapter 21, right? Chapter 21, problem 35. So we have arrayed on a semicircle, and I think the geometry is pretty clear. Let's go ahead and draw this carefully. So we have an X and a Y axis, so there's our coordinate system. We have at the origin, all of these charges are the same. They're Q, let's say they're positive Q. At the origin, and then a distance R, and then another distance R on that side, and then around the semicircle of radius R, we have charges here and here. I'm assuming these are at the 45 and minus 45 degrees. Yeah, equidistant from the 5. So yeah, these are all separation distances R from here to here and here to here. So what was the question? Find the force on charge Q, locate equidistant from the 5 other charges. Aha, this is lowercase q, and all of these are uppercase Q. Let's just say they're all the same. Okay, so this is great. We can make use of symmetry. So the force due to this upper one here is directed that way because it's a central force. The bottom one directed that way. Clearly these two vectors cancel exactly. Okay. Now all of the vectors that I'm going to attach from here could just as well be field vectors as they could be force vectors. Okay. Now, from this one here, right, notice it's the same length, so we have that to the right, and these here, you have to use a little geometry, they're going to be the same length, like that, those two. So what is the net force? First of all, the net force, in terms of its direction, we can see these two cancel. The y components of these two diagonal ones also cancel, so there's going to be a net force in the x direction. It's going to be this one here, so you're going to have k q over capital R squared is going to be this contribution here. The other ones are going to have the same magnitude times, depending on how you define the angle, either a sine or a cosine. Okay, so it'll be two of the same magnitude. This magnitude times the cosine of whichever angle, I'm not going to tell you, you guys figure that out. Okay, so that's the fundamental quantity there. The resultant is going to be, I'll just write here, etc. in x direction. So that's purely a vector addition type of problem right here. So it's a good one. And that allows me to go to another quantity called the dipole. So yeah, I'll send this up. This one we have to do carefully. So I was talking about neutral bodies, and if I have two charges, a plus and a minus, then if looked at from a great distance, that's neutral. But there is some structure in there as well. So yeah, this dipole is an important and interesting object. Let's see. We're still numbering things? Yeah. So the dipole is going to be an example of this superposition. We call this point 13. The electric dipole and let's see how we're going to orient it. Let me consult my source here. Good. We're going to put the plus on the left. So here we go. Let's go ahead, orient like this. Got ourselves an x and y axis, and we're going to put a positive charge and an equal negative charge spaced like that, so that the separation distance is a on both sides. Okay, distance, so it's minus a to the left, positive a to the right. And now we're going to ask about the field here at some point P. So what is the field, E field, at point P? Question mark. Well, here we've got some colors we can talk about this. Remember, this was I'm going to put point P a little bit lower so that I've got more room to draw. So I'll put it right here. There we go. Okay. So first of all, the field due to this positive charge here, it's a central force, so you just go in this direction and it's pointing like that. The field of the negative charge is towards the negative charge. Otherwise, it's the same magnitude, so it's the same vector here directed towards there. Now, because of that, the y components of these two vectors cancel exactly, and the x components, they're the projection twice. So the x component ends up in that, to that point there. So even though this is neutral, right, it's a neutral object, it still retains some influence, and what we want to do is do a bit of a calculation there. Okay. So the E field, so E equals, what is the E field at this point here, and we'll get a general expression for it. So the magnitude is, first of all, just K Q over this distance squared. Okay, the distance of my little dotted line squared. But my little dotted line is the square root of, we're up here on the point Y, square root of A squared plus Y squared squared. Okay. KQ over distance squared. So that's the magnitude of this one here. We need its projection to the right, so we have to define an angle. Now if I define my theta, here A is right there, I need some room for that. If I define my theta right there, okay, then I see it up here again, and my projection is a cosine of theta. So times the cosine of theta, and I have two of those. So this is going to be E sub x times 2. I'm just constructing the thing right now, so we're fine. So the E sub x is that, and of course E sub y cancels out. So the question is, what is the cosine of that angle there? We can go down here again. The cosine of the angle, where cosine theta is going to be the projection A divided by the hypotenuse. So that's A divided by root x A squared plus Y squared. And so if we put all these things together, what do we get? We get E sub x is equal to 2kq 2kq. In the denominator, I have root A squared plus Y squared to the third, so A squared plus Y squared to the 3/2. And then I have A in the numerator. So let's analyze this a little bit more. Needs more room. So directly underneath here, we're going to, I'll erase this. Just see what that means. Yeah, the 2 I'm going to, okay. So E sub x, let's do it this way. K, Q, I'm going to put the 2a in parentheses because the 2a is really the important quantity. It's the separation between the two charges, right? The way I built it, 2 times a, so that's their separation. And we've got this A squared plus Y squared to the 3/2. Well, yeah, the important point is that we only have that direction there. So the dipole has this interesting field with a certain direction. But let's analyze this right now. And let's analyze this for y being much greater than a, okay? Because now this dipole, we're thinking it's actually a pretty small object. If they were really close together, we'd think they're neutral somehow, okay? So we're going to take the limit of y is much greater than a, which means we can neglect the a in the denominator, and we just have y squared to the 3/2 is just y cubed. So this goes to kq separation divided by y cubed. So what did we start with? We started with a 1 over r squared law, but in combination we have a 1 over r cubed or y cubed law, which means the dipole field gets very weak. It gets weak much faster than the Coulomb field itself. But it's nevertheless an important effect. So right here, I'm just going to put a note, 1 over y cubed, much smaller than 1 over y squared at large distances, right? At large distances. So yeah, the dipole is a really interesting object. We're actually going to find a magnetic dipole later on in the semester. So let me do something now. I'm going to write field lines of the dipole. So field lines of the dipole, and we'll again start with the plus and the minus. That's all. I'll just draw them with a circle around. We've got a plus and a minus here on some axis. Now, to the left of the pluses are going to dominate. Okay? That is to say, to the left here, we're going to have field lines. And by the way, field lines are just lines that join the whole set of many vectors. Let me draw them first. Okay. We saw that up here, we have vectors that point in this direction, and they're getting weaker as we go further away. Okay. How about down below? It's actually going to be the same argument as above. So they're going to be pointing this way and getting weaker. On the other hand, here we have vectors pointing away because the minus is further away than the plus. Okay. On this side, the minus is closer than the plus, so we have vectors pointing this way. And yeah, you can spend a lot of time doing this. I want to draw what the upshot is you get field lines. So this is the classic dipole field. And I'm going to draw some arrows here in a moment. A very interesting lab where we actually chart these things out. Okay, so the arrows, so these are the lines where you join together all the field vectors. The meaning of it is still similar to the field vectors, namely if you put a test charge here, it's going to feel a force in the direction of a little arrow that's tangent to the line. Okay. And so we go ahead and draw these arrows here. They're important. What you say is the field lines leave the plus charges and they arrive at the minus charges. Okay. So we actually have interesting labs where we map these out in the lab. Good. So we got the field lines of the dipole, and later on in the semester we're going to have magnets that will actually show these same field line structures. We do a couple more here just to make sure you see they're leaving this way, coming in that way. So field lines of the dipole, really important. And this calculation was just showing what we have, you know, up along here. They're all crossing in this direction. Okay, so that's nice. Let's see where we're going to head with this. I'll consult the clock. Good. So after this, we see we have a lot of work to just construct field lines with two charges, and you could ask yourself, yeah, what if you have a whole lot of charges? It turns out if you have a whole lot of charges, you can get very simplified field situations. And the next chapter is going to do a lot of that, but I'm going to start talking about it here. Good. Send this up. Because what we would like is a uniform electric field. And I'll point out how that's obtained, and the proofs we'll do in the next chapter. So 14, 15, what about uniform electric fields? You see, these point charge electric fields are anything but uniform, right? They're radially in all different directions, and they get weaker the further away you go. If I wanted a uniform electric field, I would want a constant electric field vector, so the same direction, the same magnitude in a certain space. And the way we get that is by, this is an end view of, say, a couple of conductors, or we can actually do it with insulators as well. What we do is we load up a bunch of charge on one side and a bunch of negative charge on the other. And if we can, think of this as plates with with positive charge uniformly distributed, negative charge uniformly distributed, then all of those little individual vectors that we're talking about, anything but the contributions that go like this are canceled. So it's that simple. You charge up some plates, uniform charge distribution on each side with positive on one side, negative on the other. Remember, the field goes from plus to minus. There you have it. Those are your E fields. That's uniform. And once you have a uniform field, you can really control the motion of particles in that field. So we're going to say we get the uniform electric field using uniformly charged parallel plates. We'll study these in greater detail later on, and we'll prove the properties that we're just claiming right now. But yeah, we'll have this uniform field in between the plates. And in fact, another interesting feature will be that the field will be uniform in between and basically zero everywhere else. Okay, so that's an interesting feature. So we get the uniform electric field, and then the next point is to talk about the motion of charged particles. Electrons, protons, but also, say, ions, positively and negatively charged ions. So the motion of charged particle in a uniform field is very basic. So here's the thing. We're going to have F, and it's going to be a vector, is equal to Q E, where we obtain this field somehow. Okay, charge particle charge Q. So this is our one equation, but if we're talking about the motion of a particle, we need Newton's law. Okay. So our second equation is force equals mass times acceleration. And if we put these two together, we really have just the basic m times a is equal to q times e, or I'll write it this way, acceleration is equal to, right, ma is equal to qe, so it's equal to q divided by m times e. Well, what do we have here? If I said I had a uniform field, that means it's a constant field. This is constant acceleration. And we know how to deal with constant acceleration. That was the early on in Physics 4a. So constant acceleration is easy to deal with. A is equal to constant and I'll just give you an application of this right away. There's going to be a couple homework problems dealing with just something this simple and talking about electrons and protons, because the way they're accelerated is, of course, pretty interesting. But if it's constant acceleration, it's going to be this simple. And the example I give will be these plates, and I'm just going to arrange them horizontally. So 15, let's look at this, 16. So we're going to have charged plates with constant E, which is to say uniform E. So let's go ahead and put them like this. And I don't even know which ones I want to have positive and negative, but we'll just, for the sake of argument, we'll have plus. Yeah, we'll put the plus on the bottom. What the heck? Positive here, negative here. So we've got this E field, uniform. And what we're going to do is launch a stream of charged particles through here. We're going to have a stream of charged particles. Okay, so I'll just put charged particles. So what's going to happen to the charged particles when they enter the field? So these are charged particles. I'm going to draw this somehow. So I've got a bunch of little pluses and minuses, a whole stream of them. And they're all zipping in this direction. What's going to happen to the pluses? Okay. We have acceleration is equal to Q over M E. So the acceleration's in the direction of the E field for the positive charges. And by the way, constant, okay, well, let's just draw this. You're going to get a parabolic arc. Right? They're going to be pushed upward, but it's just going to be the parabola. And if we do the negative charges, so the pluses will go here, the negative charges will go down like that. Okay. So what this field will do is it will separate the positive from the negative. The positive will go flying up this way, the negatives will go flying down that way. Just to make this concrete, so if we have an X and a Y axis, okay, and then we want to have A is equal to Q over M. Let's write it this way. Let's write it this way. A sub X is equal to 0. A sub Y is equal to Q, which is the charge on the particle, over M, which is the mass of the particle, times whatever this field is. Okay. And then you can just do kinematics with constant acceleration. Constant acceleration kinematics. Okay. Because the dynamics has been taken care of, and now we're just talking about the accelerations. So what do you have? You would have x is equal to b0t. That's the x coordinate of these things. But y is equal to, well, they're coming in horizontally, so we got nothing there, is equal to 1/2 a. You know, I'll just write 1/2 a because we have what going on there, 1/2 a sub y t squared. And again, depending upon the sign of the charge, you know, you get the different sign of this. Okay, you get a different sign of A sub y. So, charged particles are separated. So this is going to affect charge separation. So I'll write that right here, charge separation, positives and the negatives. So there you have a device. You already have a device for separating charges. I think I'm going to leave it right here and assign a homework problem. I see I put a star on one, which means it's difficult, but what I'll do is I'll do a review of these problems and the previous assignment maybe next time, because I think enough will have accumulated. So anyway, for homework number 9 for this lecture here, we are in chapter 21, and I have 40, 51, 52, and 81. 40, 51, 52, and 81. These are the two problems with this topic right here that we're talking about with electrons and protons. I gotta, probably plug in some numbers. It's about 40. What was 40 all about? Ah, yes, 40 is really interesting. And 81 is interesting as well, advanced. So yeah, we'll talk about those. You guys have a good look at them. See you all next time.